So I had to come up with something. What I came up with is that existential physics is about those aspects of physics that concern human existence. Where do we come from? That concerns the beginning of the universe. What are we made of? That's the structure of matter. What can we know? Are there limits to knowledge that come from the structure of those fundamental laws? What can change? And maybe some others. So when I wrote this book, I noticed that I was constantly using the phrase "for all we currently know," for all we currently know this, for all we currently know this. So in the end, I just decided to put this into the preface, and I wrote, everything I say in this book should come with the little asterisk, this is for all we currently know. And the same is the case for what I say in my talk, unless I explicitly say it's a speculation. It's just for all we currently know. And as it goes in science, it might always be that there'll be more evidence coming in at some point, and we'll understand a little bit more, and the story would change. Okay, so I start with the question, does the past still exist? Which is basically, I think, the question that this young man asked me 4 years ago. So I think the answer is yes. So why do I think this? Well, this is really an insight that came from Albert Einstein. So Albert Einstein came up with this theory of special relativity, which is based on the idea that time is a dimension. So time used to be some kind of universal parameter. So we all shared the same moment, the same passage of time. There was a universal now that we could all agree on. This was in the days before Einstein. And then Minkowski figured out that actually this idea that time is a parameter, a universal parameter, doesn't really make a lot of sense if you look at Maxwell's equations of electrodynamics. So he figured out that those equations have a particular type of symmetry. So it's kind of similar to when you take a ball and you rotate one direction of space into another and the ball doesn't change. And Maxwell's equations also have a symmetry if you rotate one dimension of space into time. And Minkowski said there's an easy way to make sense of this. We just combine space with time, and then we can rotate in space-time. And that explains why Maxwell's equations have this structure. It's got nothing to do with electrodynamics. It comes from the structure of space-time. But what does it mean? Well, it took Albert Einstein to figure out what this means. And his theory of special relativity is, roughly speaking, based on these 3 starting points. Time is a dimension, and we live in this 4-dimensional space-time, 3 dimensions of space, 1 of time. The speed of light is finite, and the speed of light in vacuum is the same for all observers. And I should also have added here probably, but you know this already, nothing can move faster than the speed of light. And all observers' viewpoints are equally valid. Now, it's kind of hard to draw 4 dimensions, but I can at least draw 2. So we have only 1 dimension of space, and we have 1 dimension of time. This is called a space-time diagram. And in a space-time diagram, if you just sit there on your chair, you just make a straight line up. So you're not moving in space, you're just going forward in time. If you move at constant velocity, you make a line that's tilted at an angle. You can't go faster than the speed of light, so the speed of light is normally conventionally drawn at a 45-degree angle. So those gray shaded area, you can't enter those. But the general curve is like some curvy line that at any point has to stay below the speed of light angle. So this looks pretty innocent, and all by itself doesn't really mean anything. But let's look at what the consequences are of those other assumptions that Einstein started with. There's the speed of light is finite. And that sounds pretty unremarkable. But it has some interesting consequences. So when you see and hear me speak, you see and hear what happened a fraction of a second in the past. So if I ask you, am I here now? How do you know? By the time you hear those words, I could already have done something else. Maybe I just disappeared. Or you may say, well, come on, this is insane. Of course you are here now. But how do you even know what now is? What are we even talking about? Now, you could say, well, just look at this diagram. Clearly, this horizontal line that we can draw, this is now. We can just all agree on this and move on with our lives. But just drawing a line in a diagram isn't physics, right? We have to come up with an operational definition. How can we construct this moment in time? How could we measure it? And Einstein tried exactly this with what he called a laser clock. It works like this. So what you want to do is you want to come up with a definition of now at a place which is not also here. So you might want to know if I am here now. So Einstein said you can do the following. You place yourself between two mirrors and you send a laser beam, one to each side. Send them out at the same time, wait until they come back. If they don't come back at the same time, you know you're not exactly in the middle between the mirrors because the speed of light is constant. It's always the same. So you move around until the photons come back at the same time, then you know you're in the middle. And once you have done this, you can tell that exactly in the middle between sending out the photon and them coming back, the photons must have hit the mirrors. So you could stand in the middle between the mirrors, look at your clock and say, now the photons hit the mirrors. So now you have a way to tell what happens now at a place where you are not, which is at the mirrors. Okay, great. So we've done it. We seem to have defined a notion of simultaneity with this laser clock. Well, here's the problem. Suppose you have a friend, let's call her Sue, who is flying by in a spaceship or what have you, and she's doing exactly the same thing. So she has two mirrors, one left to her, one right to her. She sends out her photons, positions herself until the photons come back at the same time, and then from this she defines her notion of simultaneity. Now you would say, this is obviously wrong, because these photons do not meet the mirrors at the same time. It takes longer for the photon to hit the mirror in the direction where she's going, so which would be this direction, so pointed in the wrong direction. So the mirror is running away from the photon, so it takes longer to get there, whereas the photon that goes into the other direction is running into the mirror, so it gets there earlier. So for you, those two events do not happen at the same time. Okay, so she seems to have constructed a notion of simultaneity or a notion of now that from your perspective just looks wrong. And to make things even more confusing, if you ask her what's going on, then she would say, well, you're the one making a mistake, because from her perspective, you're the one who's moving and your mirrors are running away from the photons. So this is all pretty weird. So what does it mean? Well, it means that in general relativity, in special relativity, there is no way to construct a notion of simultaneity that does not depend on the observer. So this entire notion of now is observer dependent, the way that physicists phrase it. So this is pretty mind-boggling already. It takes some time to wrap your head around. But it actually gets worse than this in special relativity, because there are some really odd consequences from this. So what this example with the laser clock shows you is that any two events that are not in causal contact are simultaneous for some observer. So first I should explain what does it mean for them not to be in causal contact. It means you cannot send any signal from one event to the other. In a space-time diagram, this just means if you draw a straight line from one event to the other, then the angle of the line with the horizontal is less than 45 degrees, because that's how we have defined the speed of light. So suppose you have some event that is not in causal contact with your birth. So this little star is supposed to be the event where you were born, and there is a supernova explosion far, far away in a distant galaxy, which is not in causal contact with the event of your birth. Well, there is always some observer for whom those two events will be simultaneous. They would say they happen now, because you can put the observer in the middle, and then you just have to adjust the velocity of the observer until the photons, the imaginary photons, you could say, this is all theoretical physics, right, would come back from the mirrors that would go exactly through those two events. And now the next problem is, if you have two events that are in causal contact, say your birth and your death, then you can always find some event which is not in causal contact with both. For example, again, this supernova, and now there are two observers for whom both pairs of events are simultaneous. So what this means is, if you are willing to accept that anything exists now which is not also here, and you believe that Einstein was right with his theory of special relativity, you're forced to accept that everything that some observer thinks exists now is equally real. And this ultimately means that everything which happens somewhere in space-time is equally real as the present moment. Okay, so that is a little bit hard to swallow. Maybe what's even more surprising is that this is a completely standard argument which we learn as undergrad students, and the first time we hear about it, everyone sits there like, what, really? And then you walk around like for 2 days thinking this can't possibly be right, but that's just the way it comes out in special relativity. It even has a name. It's called the block universe, because the universe just sits there. It's there already. We just haven't seen the future, basically. Now, there is a little asterisk that I have to make here, because you've probably all heard of quantum mechanics. So quantum mechanics is a little bit more complicated than this, but to make a long story short, quantum mechanics is still compatible with special relativity. So the key argument that I just made doesn't really change. The major difference in quantum mechanics is that it has an indeterministic element, so you could say that the future isn't actually fixed because there's some random chance in the time evolution, but the arguments would still go through for the past, which is where I wrote, the past still exists, about the future, well, I don't know. Okay, so does the past still exist? For all we currently know, yes. That just comes out of Einstein's theories.